So chapter 3 has been about determinants and finding determinants. We talked about how if we have a determinant of 0, we have a singular matrix, which means it doesn't have an inverse. Whereas if we have a determinant that's any number other than 0, then that matrix will have an inverse. So now we're going to talk about applications of the determinant. And we're going to see two applications. We're going to see one about another way to find the inverse of a matrix. And then we're going to talk about Cramer's rule, which is a way to solve a system of equations. And that's actually going to be vital if you take differential equations next semester. Cramer's rule will come back up. So let's talk about the adjoint and finding inverses. So up until now, we said if we wanted to find an inverse, we took A, we paired it with the identity, we did some row operations, and we got the identity on the left and we got A inverse on the right. So that's a great way to find the inverse, but this is going to give us an alternative way if we want to. And there are benefits to both ways. So remember when we talked about cofactors, we said that the cofactor of a matrix is defined to be the sign, which was -1 to the I plus j. I is the row, j is the column that we're taking out, times the determinant of the matrix that we get from deleting the ith row and the jth column. So we can take that, and that's going to boil down to be some kind of number. Remember, a determinant is just a number. It's either going to be a positive number or a negative number, depending on what happens with that determinant and the sign of that determinant. So we can take and find cofactors for every item in the matrix. And we can create what's called a matrix of cofactors. And if we take that cofactor matrix and we find the transpose of that, the transpose of that matrix is called the adjoint. Now the adjoint can be used to find the inverse. And Theorem 310 tells us how to do that. It says if A is an n by n invertible matrix, then the inverse can be found by 1 over the determinant of A times the adjoint of A. So this is just another way to find an inverse. So let's see if we can apply that to this problem. We have a 3 by 3 matrix here. To find the inverse using this method, we need to find the determinant and we need to find the adjoint. So let's start by finding the determinant. And this is where you may want to pause the video, try it yourself, and then we'll come back and we'll compare answers. We could do row expansions, or we could use the shortcut since this is a 3 by 3. There's no zeros anywhere in that matrix, so you could expand along any row or any column. You'll have the same amount of work. I'm going to choose to use the shortcut method here. So I ended up with a -75 here. So now let's find the adjoint. Now we're going to have 9 different things we need to find. So if we were to look at this problem, we're going to find that first cofactor is going to be C11. That happens when we take out that first row and that first column. And remember what the cofactor is. The cofactor is the sign. So we're taking out the first row and first column times the determinant of what's left over. So we're not including that -3 where that row and column intersect. It's just the sign times the minor. So in this case, we're going to have -1 squared, which is a +1. So it's going to be +1 times 5 minus negative 18, which is going to give us a 23. So there's our C11. So I'm going to box that guy in. So now we're going to find C12. So the cofactor that corresponds by taking out that first row and that second column. So we need the sign. So it's negative 1 to the first row, second column. So 1 plus 2 times the determinant of the matrix 4, 6, 2, 1. So negative 1 to the third power is going to be a negative 1. And then we're going to have 4 minus 12. So negative 1 times a negative 8 is a positive 8. So there's C12. And then we need to find C13. That's going to take out first row, third column. So we need the sign. Times the determinant of the matrix 4, 5, 2, negative 3. Negative 1 to the fourth is a positive 1. Negative 12 minus 10 is negative 22 times the 1 is negative 22. So we've expanded along the first row. Now we've got to go along the second row. So C21. So it's negative 1 to the 2 plus 1, second row, first column, times the determinant 2, 1, negative 3, 1. Negative 1 cubed is a negative 1. 2 minus negative 3. We're going to get negative 5. C22. So now we're taking out second row, second column. Negative 1 to the fourth is a positive 1. We're going to get a negative 5 for that. And then C23. Take out second row, third column is the sign. Times the matrix, determinant of the matrix, negative 3, 2, 2, negative 3. So this is going to be a negative 1 times 9 minus 4, which is a negative 5. So then C31. So we are now taking out that bottom row. So we have negative 1 to the 3 plus 1 times the determinant of 2, 1, 5, 6. Negative 1 to the fourth is a positive 1. C32. Take out that bottom row in the middle column. So we have negative 1 to the 3 plus 2 times the determinant of negative 3, 1, 4, 6. Negative 1 to the fifth is a negative 1. Negative 1 times negative 22 is a positive 22. And then C33. So we have negative 1 to the 3 plus 3. We have taken out the last row and the last column. We're left with negative 3, 2, 4, 5. Negative 1 to the 6th is a positive 1. So our cofactor is negative 23. So we have found all of these cofactors, so we can build our cofactor matrix. So the cofactor matrix will list C11, C12, C13. It's just putting those in their respective places. So then this matrix for us will look like this. 23, 8, negative 22, negative 5, negative 5, negative 5, 7, 22, and negative 23. So the adjoint is the transpose of that. So the adjoint would be interchanging the rows and columns. So there's our adjoint. So then our inverse, I'll come over here to write that, is going to be 1 over the determinant. Our determinant was negative 75 times that adjoint matrix. And so I'm going to go ahead and distribute that negative 1 over 75 in. So we're going to have negative 23 over 75. The 5 over 75 reduces to 1 over 15. Then we have negative 7 over 75. Negative 8 over 75. One over 15. Negative 22 over 75. Positive 22 over 75. 1 over 15. 23 over 75. So there's our inverse matrix. So if we would have done row operations, we would have gotten the same inverse matrix. Inverse matrices are unique. When would you want to use this is probably now the question that you're asking. Well, this one would have been a little tedious to try to do row operations on. I'm not going to do that in the video, but you could try it on your own. Getting a 1 in that top left-hand quarter means you're going to get fractions straight away from the beginning. So, you know, this one could get a little tedious. If you were programming something, let's say you were creating a program to find the inverse matrix because maybe you needed to solve a system of equations, this may be a better way to do it because it could eliminate some round-off error. When you create programs, remember, it's not going to remember the fraction, it's going to remember the decimal representation of the fraction. So the more iterations you do with decimal representations, the more round-off error you introduce into the problem. And with this, we're finding determinants, so we're never really having to deal with fractions at all in this problem until that very end, which means we really aren't introducing any kind of round-off error, which is kind of nice. So we're always thinking about that big picture. So that's one application, is that we now have another way to find an inverse, which would be useful if we have something that could end up being a very messy inverse with lots of not fun fractions. Another application, this is one of my favorite ones, is Cramer's rule. So Cramer's rule is a way to solve systems of linear equations using determinants. Now, if you take, and I alluded to this earlier, if you take differential equations next semester, we will use Cramer's rule. It will come back. Only our determinants won't be numeric. They'll actually be functions. So that's kind of cool to think about that. So, but for now, we're going to stick with numbers. So let's say we want to solve a system of equations. And we're going to look at 2 equations and 2 unknowns, and then 3 equations, 3 unknowns. So with 2 equations, 2 unknowns, we're talking about in terms of x and y, so 2-dimensional space. We can create what I like to call a D matrix, where it is the coefficients in front of the x and y. Let me write it over here. And then I like to create a dx and a dy matrix. So dx replaces that x column with what's on the other side of the equals. So we're going to have s and t here, and then b and d. dy does the same kind of thing, only to the y column. We are now going to replace that y column, which would be here, with what's on the other side of the equals. So we have AC and then ST. So that's where this stuff is coming from. So then X ends up being dx over d. Y is dy over d. So this matrix, they have STBD. I call that dx. And that matrix in the denominator, I call d. Now, this will work as long as the determinant's not 0. If the determinant's 0, we're dividing by 0, and that creates a whole other set of problems, which means you're either going to have an infinite number of solutions or you're going to have no solution. Now, if we can actually do the same thing in 3 dimensions also, by creating your D, which is still your coefficient matrix, and then replacing that x column with what's on the other side of the equals. So this system of equations looks like this. So then our D matrix is that coefficient matrix. So then dx would replace that x column with what's on the other side of the equal. So that's where this column's coming from. Just like we did up there in 2 dimensions. dy is going to replace that middle column with what's on the other side of the equals. So that's where that's coming from. And then dz replaces that z column from d with what's on the other side of the equals here, which is where that's coming from. So everything works pretty much the same way. So Cramer's rule works great if there is one solution. So if we get a unique solution, which means in 2 dimensions where we have 2 lines intersecting, in 3 dimensions we have 3 planes intersecting, and they're intersecting at one point. It falls apart a little bit if we have no solution or if we have an infinite number of solutions. So let's look at what would happen with Cramer's rule. So if D is equal to 0 and at least one of the determinants is different from 0, then the system is inconsistent, which means no solution. So we could write empty set, or we could write the empty brackets, or we could just say no solution. Okay, so if D is equal to 0, and then they're talking about 3 dimensions, this would apply in 2 dimensions too. So at least one of the other ones is something other than 0. So you could get 0 for, let's say, this one and this one, but then this has to be some kind of number other than 0. Then that means you're going to have no solution. Now, if everything is 0, so that d is equal to 0 and all of the determinants dx, dy, and dz are equal to 0, then it's consistent dependent, which means infinite number of solutions. So then how would you write that? Well, this is where you would have to go back to RREF. You would have no choice but to go back to augmented matrix, doing row reductions, coming up with what that RREF form looks like, and then that will tell you what the solution would be. You just can't get that final solution using Cramer's rule. This would just tell you, yes, there's an infinite number, but it doesn't tell you how to find the answer. What I really want to focus on is the consistent independent case where you're going to have a unique solution. But I wanted you to see that some wonky things could happen, and you can determine whether or not you're dependent, consistent, or inconsistent, depending on what you get. So let's put all this to practice. Let's look at this one. I'm going to call this one number 1. We want to solve this system. So we're going to find our D matrix. So D is going to be that coefficient matrix. And then we're going to find that determinant. So that determinant is going to be 15 minus negative 45. Just kidding, 75. And 15 minus negative 75 is 90. So there's D. So dx is going to replace that first column with what's on the other side of the equal. So my first column in this matrix would be 3 and 21. That second column remains the same from D, so negative 5 and 5. So we're going to have 15 minus negative 105. And that's going to be 120. And then dy is going to replace that y column. So the 315 column stays the same, but now we're going to plug in 321. So we have 63 minus 45, and that's going to be 18. So we found 3 determinants. X is found by taking dx divided by d. So dx is 120 divided by 90. And 120 divided by 90 is 4/3. Y is found by taking dy and dividing by d. So dy is 18. 18 divided by 90 reduces to 1/5. So our solution is the point 4/3 and 1/5. So if we look at that second one, I'm going to call this problem number 2. We have 5x minus y is equal to 13. 2x plus 3y is equal to 12. So let's solve that one. So it's going to work the same way. So d is equal to the determinant of 5, negative 1, 2, 3. So 15 minus 2, 15 minus negative 2 is 17. dx replaces that x column with what's on the other side of the equals. So we're going to have 13, 12 for our first column. And then negative 1, 3. So our determinant is 51. And then dy replaces that y column with what's on the other side of the equals. So 5, 2 is the first column, 13, 12 is the second column. So x is equal to dx over d, which is 51 over 17, which is 3. And y is equal to dy over d, which is 34 over 17, which is 2. So we have a consistent independent system. X is 3, y is 2. These two lines cross at the point 3, 2. So I want to do just a couple more. I'm going to call this one 3, then 4, then 5. So if we look at problem 3, there's our system. So let's set our matrices up. D is equal to this matrix. And we want to find the determinant. So when I found it, I got 0. Dx is going to replace that first column with what's on the other side of the equals. So I replace this column with this stuff. Those other two columns stay the same. And I got 0 for that one. Dy is going to replace now that middle column. Everything always goes back to D with that. And I'm cheating on these. I'm plugging these into the calculator. And I'm letting the calculator do the work. And we're going to get 0. And then DZ is going to replace that third column. And I got 0 for that. So this is one of those weird ones. We ended up getting 0 for everything. So 0 for everything means it is consistent and it's dependent. So we have an infinite number of solutions. So the only way we can solve this is to actually do row reductions. So we're going to take that augmented matrix and we're going to do some Gaussian and Gauss-Jordan elimination. And I'm going to cheat on this again. We've had a lot of practice with this up to this point. So if we were to pop this guy into the calculator, or if we did it by hand, we would get the same thing. So there's our RREF form. So what this is saying is that x1 would be equal to 1/7 x3 plus 1/7. So I went ahead and added this term to the other side. x2 would be equal to 11/7 x3 minus 3/7. And then x3, I'm going to let be the free variable. So there's how we would express this. In three dimensions, what's happening here is we have 3 planes, and all 3 planes are intersecting on a line. And that's the equation of the line of intersection. So that's one of those fun ones. Let's look at number 5. So number 5 is a system x plus y minus z is equal to 6. 3x minus 2y plus z is equal to -5. And then x plus 3y minus 2z is equal to 14. So this is where you may want to pause the video and try this one and the next one yourself, and then come back and compare your answers. So there's our D matrix. That's your coefficient matrix. The determinant, I got -3. So now we're going to find dx. We're replacing that first column. I found that to be -3. dy replaces the second column of D. And then dz replaces the last column of D. So x is dx over d. So -3 over -3 is +1. Y is dy over d. -9 over -3 is +3. Z is dz over d. So 6 over -3 is a -2. So there's our x, y, z. And then that last one, matrix D is the coefficient matrix. I got 22. dx is going to replace the x column. Notice this is a homogeneous system because each equation is set equal to 0. I got 0. There's 0. Anytime you have a column or a row of zeros, the determinant's going to be 0. And we're going to get 0 for that determinant. So in this case, we ended up with x is equal to dx over d. Now notice d was not 0. D was 22. So we're going to get 0 for x. And we're going to get the same thing for y and z. The only solution to this is the trivial solution. So this one has a unique system. or excuse me, a unique solution.